Here we're going to start and begin our basic circuit analysis. Let's look at some definitions in which we have a circuit consisting of electrical devices that perform a useful function. And so keep in mind, a key important concept is that when you look at electrical devices such as a resistor, capacitor, inductor, think of what its purpose is. What function does it serve in the circuit? Next, we're going to take a look at basic circuit analysis tools like Kirchhoff voltage law and Kirchhoff current law. And then we're going to introduce some electrical devices that control voltage and current. So we're going to start off with element constraints, such as a resistor. So here our objective is, given a two-terminal element with one or more electrical variables specified, use the element IV constraints to find the magnitude and direction of the unknown variable. So there is a relationship, sometimes linear, sometimes nonlinear, associated with the device, what we call the IV characteristics. So let's say we have a voltage and current reference marks for a two-terminal device. So here I have a device, okay, and as we mentioned before, when we identify a reference current I, we have a plus and a minus, and that's our voltage across this device. Remember, voltage requires 2 points that measures the voltage across this device, whereas current is a through variable which measures the current through this device. Now symbolically, let's say we can take a resistor R, and this would be our symbol for a resistor, a plus, minus, a V, and a current I. Now associated with this resistor is the IV characteristics given as Ohm's law. That is, V is equal to IR. We can think of R as a proportionality constant, such that when my current is increased, my voltage is increased, and when I double my voltage, my current is doubled. So that's what we mean by a linear device, and the amount of the slope of the IV characteristics shown here in this graph, I and V, we have a resistor that's linear across this device, and we see the slope here. So this is like the rise over the run, or delta I over delta V, which is basically the slope, and in this case it's 1 over R, and 1 over R is also known as the conductance. So the slope of this IV characteristic is resistance. So that's how we characterize our device, and we define this as our linear range. Now some devices may go nonlinear, like so, okay, and we just basically, and for the purpose of this introduction lesson to circuit analysis, we'll just consider the linear range for the moment. So that's what we mean by a terminal device, in which we have a resistance governed by the current and voltage characteristics for this device. So here's our voltage and current plot. Now I could easily exchange between these two axes, but for this purpose we'll just label here the vertical axis as current and the horizontal axis as voltage. And the slope of this line is our conductance, which is equivalent to 1 over R. So let's go through this example. We have a resistor operating as a linear element as long as the voltage and currents are within the limits defined by its power rating. Now suppose that we have a 47 kilo ohm resistor with a power rating of 0.25 watts. What we want to determine is the maximum current and voltage that can be applied to the resistor and remain within its linear range. Since this is a resistor, we can use Ohm's law. That is, V is equal to IR, and we note that power using this would be V squared divided by R, and current is equal to I squared R. Now usually when I denote cap letters, that denotes that it's a DC current. If I use script letters, that is known as an AC type of variable. Alright, so now we can solve for I. We'll call this I max. Is equal to P max divided by R. And then that's a square term right here, which implies the square root I max is equal to the square root of P max divided by R. Now all we have to do now is substitute, and we recall that P max from here is 0.25 and the resistance is 47 kilo ohms. So what we'll do is substitute, which is just the square root of 0.25 watts divided by 47 kilo ohms, which is 10 to the third power. Okay, and that yields 2.31 times 10 to the minus 3 amps, which is equal to 2.31 milliamps. So that's our maximum current for this device. Similarly, for the voltage max, we can just also use Ohm's law if we want, just divided by the resistance, but we'll use the power equation just for practice. So this would be square root of R times P max. And that's using this relationship here to get this relationship. In that case right here, this would be 47 times 10 to the third times 0.25, which is equal to 108 volts. And if I multiply I max times V max, that should equal to 0.25 volts.